This video is going to discuss the concept of limiting reactants, and these calculations can be more difficult than others. It's wise just to keep your head on straight and think clearly. I'm going to show you a technique for determining limiting reactant. First of all, a limiting reactant is the one that is used up first, and when it's all used up, it prevents more product from being produced. So we have to first determine which reactant is limiting. Well, how are you going to know if it's the limiting reactant problem? Well, the amounts of each reactant, or of at least two reactants, are going to be given. So it's pretty easy to see. Here's an example.
Enter the sandwich shop. Click Sandwich Shop to enter. Complete sandwiches are made by combining one piece of meat with two slices of bread. Click the Make Sandwiches button. The sandwiches use all the meat, leaving excess bread. Now view the limiting reactant for NO2 molecules. Click the Limiting Reactant button. Product molecules are made by combining reactant molecules in the correct proportion. Click the React button.
So here we have chemical reactants. We have NO molecules, we have oxygen molecules, and we're going to look at how many we have. Notice that 4 are given for NO and 3 are given for O2. So which one's going to run out first?
NO is the limiting reactant and is completely consumed. Excess oxygen remains after complete reaction.
So we're going to have a limiting reactant and an excess reactant in our problems. We're going to do an example here where we start with 2,000 grams of a substance, methane, and 2,000 grams of water, and we're trying to see how much product is produced from this reaction. So I'm just going to label my work here. I have 2,000 grams of methane and 2,000 grams of water. Now you're thinking, oh, it's the same amount, so we're not going to run out of either one of them. But remember that the gram amounts are not relevant. It's really the mole amounts that matter. We're looking for an amount of carbon monoxide that's produced. I'm going to show you a quick technique that I think really helps us understand the concept of limiting reactants when we're first starting. And this is to start with gram amounts of each of our reactants individually. What we're going to do is we're going to do a redundant calculation where we calculate how much product we would get from either one of these if we had excess of the other reactant. So what I'm going to do is convert from grams to moles for methane. You have, in every stoichiometry calculation, you need to have a balanced equation, which we have right here, and you have to convert your given into moles if it's not already in moles, and here it's not. The molar mass of methane is 1 carbon and 4 hydrogens, and it's 16 grams per mole. And that will be the calculation there. We're going to convert now from moles of methane, CH4, to moles of what we're looking for, which is CO. And it is a 1-to-1 mole ratio. The last calculation is to convert from moles of CO, let's say, to grams of CO. It's the amount of the product. Here, for every 1 mole, we have, let's see, 1 carbon is 12, plus oxygen is 16, so this is 28 grams per mole. If I were to calculate this, 2,000 times 28 divided by 16, I would get 3,500 grams of carbon monoxide. Okay, I need to compare it to the answer that I'm going to get from the example below. So the first thing is to convert water from grams into moles. And for 1 mole, it is 18 grams. Now for water, I need to convert from moles of water into moles of carbon monoxide, and it is again a 1-to-1 mole ratio. From the balance equation, there's a 1 implied here and a 1 implied here. And the last step would be to convert from moles of carbon monoxide to grams. You know, this last step that I'm doing probably isn't necessary because it's the same, 28 grams here and 28 grams here. So I would have known my answer without actually converting to grams. So 2,000 times 28 divided by 18. 2,000 times 28 divided by 18. And I get 3,111 grams of carbon monoxide. Now, what is the correct answer? Because they're both the same thing. They're grams of carbon monoxide. Well, it's the smaller amount. Because remember, the limiting reactant is the one that controls the amount of product. Well, it's not possible to make 3,500 grams of carbon monoxide because once you make 3,111, you're going to run out of something. Now, what do you run out of? This is the limiting reactant, the one that has the smaller answer. And so water is my limiting reactant. That's what I'm using for this symbol here. And methane is the excess reactant. I'm using that for excess. And so this calculation just shows us which one was limiting. There's other ways to calculate. This is just one method. Here's another example. 49 grams of ammonia and 89 grams of copper react according to this reaction. And we want to find out how much copper is produced. Again, I'm going to do this in grams. Okay, grams of copper. So that's what I want to find out. And let's see, 49 grams and 89 grams. What we're going to do is we're going to start the same way, convert each of our givens into moles. Because the gram amounts are not the things that tell us which reactant will run out first. All right. So here we're going to convert from grams to moles. This is grams of NH3 to moles of NH3. And this is 1 nitrogen, 3 hydrogen is 17 grams. And then grams cancel out. I'm also going to convert from moles of NH3 to moles of the product I'm looking for, which is copper. This is a mole ratio of 2 of these to 3 of these. And I'm just going to stop here because this will show me which amount is smaller for moles. I'll get you caught up at the end, I guess is what I'm trying to say. Now I'm going to move down to the bottom example. And for every 1 mole of copper, it is, well, let's see, copper is 63.5 plus oxygen, which is 16, so it's 79.5 grams. And that cancels out. And from moles of copper to oxide into moles of my product, which is just copper, it is, let's see, a 3 to 3 mole ratio. All right, we'll do both of these calculations. So at the top, 49 times 3 divided by 17, and it would produce 8.65 moles of copper oxide. The one on the bottom, notice that we have in the mole ratio 3 over 3, so I can actually just cancel those out. So in the bottom it's 89 divided by 79.5, and this would make 1.12 moles of copper oxide. Oh, I'm sorry, that's not the correct label. This would be copper here and just copper here. Maybe I can erase that. There we go. Okay, so now what do these numbers mean? Remember, it's a smaller one that comes from the limiting reactant. So this isn't possible. I can't make 8.65 moles of that. So that's not going to work at all. That was the excess reactant, which was NH3. This is what we run out of first. Copper to oxide runs out first because of the smaller answer. Now we've got to take this number and convert it into grams because that was what the answer requested, or the problem requested for our answer. So 1 mole is 63.5 grams. That cancels out. And our answer here, 1.12 times 63.5, I'm going to write it above up here, is 71.1 grams of copper produced. Alright, so this is just a quick way to try to determine which reactant is limiting. It's the one that gets all used up and it controls how much product we can get. If you have questions or if you have additional requests in class, I'd be happy to go through some more examples. Thank you.